Okay. I show one more example. Let us suppose you have got things like this, some numerator polynomial, but denominator if you factorize, you have one factor say which is occurring twice. So, its square is coming, another is say this. Then we say this has pole at z equal to 1 by 3, but pole order of the pole is 2. It has a pole at z equal to 1 by 6, but order of the pole is 1, because this factor has a power 1, this factor has a power 2. So, pole at z equal to 1 by 3, but that has order 2, second order pole at z equal to 3. That means a factor like this 1 minus 1 by 3 z inverse, pole at z, not at z equal to 3, z equal to 1 by 3. Because if you put z equal to 1 by 3, inverse of that cancels with 1 by 3, you get 1, 1 minus 1 0, division by 0, which means the pole. It is a second order pole, because the power factor is getting repeated. So, there is a power of 2. We say there is a pole of Hz has a pole at z equal to 1 by 3 of order 2, second order pole, and it has a first order pole at z equal to 1 by 6. First order second order okay. This to factorize, you see, we would have a by as before 1 minus 3 z inverse, then b by, we will have this again. Why I will explain. So, this factor here the factor is squared, and then c by the other factor. Why? Because if you do not have this, then denominator will be product of the 2, but here you have got power of 2. So, this must be present. How about this? This is okay, denominator will be product of this, you get this kind of form, but along with these two, even if I have a by the first order factor, still denominator will be this product, okay, because it is the LCM of the 3 factors, 3 terms. Okay. So, this and square of this square of this, and then this. So, denominator will be this into this, which is this. So, we have to have a provision for this also, this kind of term also, because this is not enough, this kind of term also is possible to exist, because even if just you have got the first order factor here, second order factor, the same factor, and this, when you are doing algebraic addition, denominator will be product of these two only. So, you cannot rule out a possibility of a term of this kind also in this expansion. This is called partial fraction expansion. Okay. If you add them, you know, you will have 1 by square okay. So, what will happen? 1 minus 3 z inverse, if you take that out, you will be getting a into okay. Then b, if you take this out, it is just and c, if you take out c into. Now, if you simplify it, you will see this will have a second order term z inverse 2, this is first order z inverse, this will have z inverse 2, z inverse, here also z inverse. So, overall it will be a polynomial where there will be z inverse terms present, z inverse 2 terms present, and constant terms present. That if you can equate with 1 plus z inverse. So, here the z inverse 2 term is absent, the corresponding coefficient you equate to 0, coefficient corresponding to z inverse you equate with 1, the constant you equate with 1, you solve for a, b, c, you get the coefficients, you have this expansion. Okay. That I am not doing. That I am not doing, but this is one way of doing it. You expand it, you write this numerator expression, okay, collect the terms for Z inverse. So, corresponding coefficient equate with 1, collect the terms for Z inverse 2, corresponding coefficient equate with 0, collect the terms for the constant equate with 1, solve, you get A, B, C. So, you get these factors, let them be as it is. Then the question is, I have got the same ROC as before. So, as far as this term is concerned and this term is concerned, I know what they will be. Here the ROC is pole is at Z equal to 1 by 3. So, either mod Z greater than 1 by 3 or less than 1 by 3. I am giving less than 1 by 3. So, I will take ROC to be mod Z less than 1 by 3 here. So, this will give rise to capital A to the power A is 1 by 3. So, capital A 1 by 3 right sided sequence. Sorry. Let us start with this C by 1 minus 6 Z inverse. Here ROC will be, because ROC cannot contain the pole Z equal to 1 by 6. So, either mod Z greater than 1 by 6 or mod Z less than 1 by 6. We have to take mod Z greater than 1 by 6. Okay. So, this will give rise to C into A to the power n u n, because it is a right sided sequence. We have seen already. C constant 1 by 1 minus A Z inverse mod Z greater than mod A. Mod A is same as mod 1 by 6, that is 1 by 6 itself. So, from our previous exercise you get this term. In the case of this A into, it will be minus A to the power n, that is 1 by 3 to the power n minus u minus n minus 1. A, B, C you already found out, but there is one more term, this will be what? This is the question. So, this I give you answer now. I will come back to that. If you have an expression like this, and obviously this has a pole, second order pole at Z equal to 1 by 3. So, this cannot be part of the ROC of this part, this fraction. Okay. So, either mod Z less than 1 by 3 or mod Z greater than 1 by 3. We are giving mod Z less than 1 by 3. Okay. So, this is what was given, mod Z less than 1 by 3 greater than 1 by 6. Okay. So, you have to take mod Z less than 1 by 3 for the ROC. That means, but now you can write this also as one system into another. There is one Z transform into another. This as ROC mod Z less than 1 by 3, because total was given to be mod Z less than 1 by 3 greater than 1 by 6. Okay. So, as I told you, ROC for each of them is either mod Z greater than 1 by 3 or less than 1 by 3, but we are giving mod Z less than 1 by 3 greater than 1 by 6 for the overall. So, we have to take mod Z less than 1 by 3 only to conform to that. So, therefore, this has mod Z less than 1 by 3, this has mod Z less than 1 by 3. So, this will give rise to a sequence minus 1 by 3 to the power n u minus n minus 1, and then this will give rise to same thing minus 1 by 3 n convolution, because Z transform if you are multiplying in Z domain, it is called convolution in time domain. This convolution you work out. Okay, this convolution if you work out, you will get the result. What is this for function? This function starts like this 1, okay, because minus and minus plus. So, you can forget the minus, it is same as 1 by 3 whole to the power n. This minus is for all samples, minus is for all samples, minus minus plus, so forget minus. Same thing. So, it starts at n equal to minus 1 onwards, n equal to minus 1, it will be 1 by 3 to the power minus 1, that is 3. okay, 1 by 3 to the power minus 1, then 1 by 3 to the power minus 2, so 3 square dot 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 at minus nth it will be 3 to the power n. Okay. This sequence, then this side is 0, 0, 0, 0, 0, 0. This you have to convolve with itself. So, if you want to convolve with itself, you have to flip it first. If you flip it, this will go here, then here like this, dot dot dot. At 1 it will be 3, then 3 square dot 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 3 to the power n at n. If you flip it, then if you do not shift, just multiply term wise, you get 0, because 0 into 0, this into 0, this into 0. So, at convolution result at origin will be 0. Okay. If you shift it further to the right, there will be no overlap. So, you will continue to get 0 values. If you shift it to the left, this 0 comes here, this comes here, still you get 0. So, even if you shift it to the left up to minus 1, if you shift by minus 1, I will shift it to the left. So, this 0 comes here, this comes here, still there is no overlap. So, you get 0. If you shift further from minus 2, then 3 comes below this. So, you have got 3 square, 3 cube, dot 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 dot. Okay, 3 square, 3 cube. Okay. This 3 comes here. So, 3 square, how many shift? 2 shift. So, that is at minus 2 you get 3 square, at minus 3 you get 3 cube, dot dot dot, at minus n you get 3 to the power n. Okay. You sum them, you get a value. Next time when you move, okay, next time when you move, this 3 comes below 3 square, 3 square comes below 3. Just a minute. Okay. So, I leave this as an exercise to you. You carry out this convolution and you get the result. Okay. Convolution between the two. Let this be an exercise. Maybe I will put it in the assignment. So, that is all for inverse Z transform calculation. I now move to the next topic, which is a very, very powerful topic, very important topic, discrete Fourier transform, DFT. All right, discrete Fourier transform, DFT. It is not discrete time Fourier transform, but let us start with discrete time Fourier transform. Originally, I had xn, one sequence, maybe infinitely long from minus infinity to plus infinity. It has a DTFT x e to the power j omega, which is a complex function. So, as I told you, if you want to really plot it, you should plot magnitude versus omega and phase versus omega, and it will be both, it will be periodic in both cases over omega over a period of 2 pi. But for our purpose, I just have one plot, and that will be enough to explain the points, but actually it is not a wrong correct thing, because I should have mod plot and phase plot, because this axis is real. So, mod is real, phase is real, right, but this is a complex number. Complex number cannot be shown by one axis. Nevertheless, just to make my point, I am just showing x to the power j omega. Okay. The whole logic will be same if you make separate plots, one the magnitude mod x to the power j omega versus omega, and at the phase this angle of this versus omega. Same logic will hold good. Just take it that way. Now, this I know it will be a periodic function, right? It might be like this. From minus pi to pi. So, if you go to 2 pi, same period will continue, same thing will continue here like this, and again here. Now, you see xn is a sequence. I have got the DTFT, either you take from here to here, one period from minus pi to pi, or you take from here to here, 0 to 2 pi. For this topic chapter, we will consider 0 to 2 pi, okay, because this is a periodic function. Any period of duration 2 pi is fine. So, either you take from minus pi to pi, or you take from 0 to 2 pi, whatever you get, repeat it again, you get the entire waveform, right. This part you go on repeating, or this part you go on repeating. Okay. If this is the period, you go on repeating it. If this is the period, you go on repeating. You get the same thing. It does not matter how you choose your period. Period is 2 pi. So, I might choose this. Okay. But whether you choose this or this, one thing, this entire waveform envelope is required. For instance, inverse DFT. Xn is there. To get xn back, what was the inverse DTFT? That is, xn was, if you from minus pi to pi, if you follow this minus pi to pi, integrate, n is your choice. You want to find out sample at particular n, carry out the integration over all omega from minus pi to pi. So, you need this entire waveform, full waveform from minus pi to pi. Then only the integral will be, you can carry out and you can get xn, isn't it? That is what we have studied so far. Now, I will make a claim that suppose xn is finite in length, that is given over say n equal to 0, 1 up to this. We call it capital N point sequence xn. That means, is given over this zone, outside this zone it is all 0. We also call it FIR sequence, because you know, I mean, if it is the impulse response of any system, linear simple system, impulse response means actually unit sample response, then it is finite in length. That is why it is called FIR sequence, finite impulse response, FIR sequence. Okay. Endpoint sequence, FIR sequence, it all means that its length is finite. Outside that window from 0 to capital N minus 1, outside that it is all 0. Within this window only you have got non-zero values of xn. Suppose xn is given to be of that kind, it is not infinitely long, it is only finitely long over this region 0 to capital N minus 1 for some capital N. So, length is capital N, we are counting from 0, 0, 1 up to n minus 1. So, total length is capital N points, we call it endpoint sequence. For this also we will have the same DTFT expression. Only thing is the summation will go from n equal to 0 to capital N minus 1, not from minus infinity to infinity, because outside that zone all samples are 0. But still it will be DTFT. To get that back, we should have this inverse DTFT, right. So, the entire waveform of DTFT is required apparently. But now I make a claim that if this is given, I will not require this entire waveform. Just some samples of this will be enough, not all the entire waveform. That is, I mean, in order to store the entire waveform, I need infinite memory, because all values, how many values? From here to here, if you go continuously, infinite values, right, omega, infinite values of omega from this range 0 to 2 pi. But if I say that if the sequence is given to be finite in length, then I am saying that I will not require this entire waveform, I will require only its samples, some samples. It has to be taken appropriately, and my claim is these samples are good enough. Okay. In fact, I will have capital N number of samples, we will see that those samples are good enough for me to get that back, get back xn. I do not need the entire waveform. So, I need only to store some samples, actually capital N number of samples. That is a claim I am making. So, I will have to justify the claim, but the claim I am making is this total zone 0 to 2 pi, right. This I will divide into some sampling points. This period of sampling point period will be 2 pi by n. So, 0, 2 pi by n, 4 pi by n, 6 pi by n dot 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 kth sample, kth will be at 2 pi k by n. Okay, this is the kth sample. This will be omega equal to 2 pi k by n. So, if k is 0, omega equal to 2 pi k by n, where k can be 0. If k is 0, omega is here. If omega k is 1, 2 pi by n, I am here. If k is 2, 4 pi by n, I am here, and dot dot dot. For any k, it is here. So, I am just sampling like this. How many samples can I get? N samples. 0th sample, first sample, second sample, like that. What will be the last sample here? This was the 2 pi case. So, this is the last sample. Last sample will be n minus 1th sample. 0th sample, first sample, because I have divided the range 2 pi into n. So, 2 pi by n, 2 pi by n, 2 pi by n. How many 2 pi by n's? This periods n times, right. So, this is 2 pi by n, before that 0th sample. Next 2 pi by n, first sample. Next 2 pi n. So, next 2 pi by n, second sample. Okay, so, capital Nth 2 pi by n period, before that will be n minus 1th sample. Okay, 0th sample 1 2 pi by n, first sample another 2 pi by n, 2, second sample 3 times 2 pi by n. So, n minus 1th sample n times 2 pi by n. Understand? I repeat again. 0th sample, you go ahead 2 pi by n. First sample, you go ahead further 4 pi 2 into 2 pi by n. Second sample, you go ahead further 3 into 2 pi by n. Then n minus 1th sample, you go ahead further, you cover this entire zone n into 2 pi by n, that is 2 pi. That is why if you count, it will be n minus 1. 0th, first, 0th sample, first sample, second sample, dot dot dot, n minus 1th sample. So, k will be 0 for 0th sample, k will be 1 for 1th sample, dot dot dot, up to n minus 1. If you make k equal to n, it will be n cancelling, omega equal to 2 pi, and 2 pi means this sample is same as original sample. Because of periodicity, this is same as this. There is a, we will not go up to nth, we will go up to n minus 1th sample. So, total will be 0 to n minus 1, which is n samples. So, here general sample at omega equal to 2 pi k by n, how much is the value? That is the DTFT at this much omega. That is, that DTFT will be x e to the power j, instead of omega, it is 2 pi k by n. So, by DTFT formula, it will be x n e to the power minus j omega n, but omega is this. So, 2 pi k by n, this much omega into small n, and small n will be over the range, but range is not from minus infinity to infinity, range is only over this. Okay. Then instead of writing it as capital X e to the power j 2 pi k by n, we in short just write it as a function of k. So, it is the kth sample, that is called kth DFT of x n. DFT means discrete Fourier transform. That is, x n is give you sequence, a finite length sequence of length capital N. I am sampling the DTFT at capital N number of points, not less than capital N. What is capital N? It was the length of the original time sequence. If the length is capital N, that many, at least that many, I could take more, but at least that many samples is required of this envelope. If I take more, that will mean that finite length sequence has further, has more length larger than capital N with extra zeros brought in. For instance, if I suppose instead of taking capital N number of samples, I take capital N plus 1 number of samples, that is 2 pi by capital N plus 1 is the period. Then it means I am considering the time sequence to be of length not capital N, but from capital N plus 1, that is 0 to capital N, not n minus 1, with the last sample as a 0. So, it will not change the DTFT summation. Okay. So, DTFT will remain same, but it will be like a length n plus 1 sequence. Anyway, to start with, assume that given sequence is length capital N and I am sampling the envelope, that is the DTFT at capital N points, which means the gap sampling period is 2 pi by n. I have 0th sample, first sample, second sample, kth up to n minus 1th. Nth is back to this. So, kth sample is called the kth DFT, which is by the DTFT formula simply this, fine. But what is the big deal about it? My point is, given this capital Xk, I would be able to get back my Xn for n equal to 0, n equal to 1 up to capital N minus 1, which means the samples are good enough for me to reconstruct Xn. I do not need the entire envelope and an integral calculation to get back Xn. So, for that we see this is given Xk, I am rewriting that same expression okay. So, now suppose instead of n I make it r, it is local index does not matter r. Okay. I want to find out x n, n can be 0, where n can be either 0, 1 or dot 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 n minus 1, because that is the range of this sequence. The sequence is located from n equal to 0, 1 up to capital N minus 1. Outside this window, this fellow is 0. So, I have to find out x n, nth sample, where n could be any of them, but you fix a n of your choice from this range. Once you fix, that is fixed. My question is how to get that x n, fine. So, once n is known, left hand side I multiply by e to the power j 2 pi k n by capital N. Okay, this k, same k I put. Right hand side also e to the power j, and this 2 e to the power I combine j 2 pi k by n, 2 pi k by n. It is small n to small n, it is minus r, right. I am just multiplying both sides. Capital X k for a particular k, there is a summation e to the power j 2 pi that k into small n by capital N. What is small n? You want to find out the nth sample x n, n is in this range. So, that n you put at this. So, right hand side also multiply by the same thing, take that inside the summation, combine the two exponentials, you get this. Then what you do? I sum this over k, keeping n fixed. So, here also this after all, if you sum, it was sum over r. So, it is a function of n also, k also. So, I sum it over k. So, this is becomes a function of n only, because after summing over k, k goes, it is a function of n. This also becomes a function of n, because inner summation was with respect to r. So, summation this becomes function of n and k, then you are summing further over k. So, it becomes a function of n. But I know whenever there is double summation, the rule of thumb is you should interchange the two summations. So, r will go out, x of r, it depends only on r. So, I can happily keep it outside, k equal to 0 to n minus 1 e to the power j 2 pi k depends on k. So, it comes here n minus r, all right. Now, small n is your choice, you have fixed n in this range, r is varying over the same range 0 to n minus 1. So, as r is going from 0 to capital N minus 1, r will become equal to small n once, and on other occasions it will be not equal to small n. So, I can write that out right hand side as r equal to 0 to n minus 1, but r not equal to small n, r equal to small n case I will write separately. So, then you have got x r summation k equal to 0 to n minus 1 e to the power j 2 pi k by n minus r as it is. But n r is changing, r is varying, but r is not equal to n. So, n minus r will be integer, positive negative does not matter, integer will not be 0, and r equal to n case, when r equal to n, it is x n, that case I am writing separately. If r equal to n, n minus n 0, it is equal to 0 1, 1 you are adding capital N times. So, capital N times x n, this is the expression, right. Now, what happens to this series? It is a GP series, this is n minus r, you can call it m, and it is m is non-zero. because r not equal to n in this summation. So, in this GP series it will be 1 minus e to the power j 2 pi k, okay, not k, is summed over k, 2 pi m by n, and we are summing from 0 to capital N minus 1. So, n will come divided by 1 minus e to the power j 2 pi. Okay. Now, look at the numerator. This cancels, e to the power j 2 pi m, m is an integer, positive negative does not matter. Okay. So, e to the power j 2 pi into an integer, that is 1. So, 1 minus 1 0. So, this is 0, but denominator small m by capital M. Small n is neither 0 and small m cannot be equal to capital N. If it is capital N, then again e to the power j 2 pi, which is 1, 1 minus 1 0, it will be 0 by 0, but that cannot happen, because what is small m? Small m was n minus r, right. N is varying from 0, 1 up to capital N minus 1, this is n, and r also varying from 0, 1 dot 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 n minus 1. So, n minus r, okay, maximally can be capital N minus 1. The difference can be this minus 0 or this minus 0, maximum. So, m can be maximally capital N minus 1 or less than that. It cannot be equal to capital N, which means e to the power j 2 pi into this factor can never be equal to 1. Okay. So, 1 minus 1 0, 0 by 0 case does not exist, arise. So, it will be something which is non-zero. For it to be 0, e to the power j, either m is 0, not possible, or m equal to capital N, that is not possible, because m is n minus r. Maximum e, either maximum n and minimum r, or vice versa, which is capital N minus 1 minus 0 or 0 minus capital N minus 1. Either case, it cannot be equal to capital N or minus capital N. Okay. So, therefore, this cannot be 0. So, 0 by something, non-zero is 0. So, this whole part disappears, which means I am left with n into x n. So, what is n into x n? This summation. Okay. This part I started with this and then I carried on. So, this is equal to n into x n, which means x n will be 1 by n into this summation. This is called inverse DFT. That is, if this k sample, if this samples, n number of samples of the DTFT are available with me, that is capital X k, capital X 0, capital X 1, capital X 2 up to capital X minus 1 are available with me, I can run a summation where k is varying. So, capital X 0, capital X 1 like that, and multiply by this factor. Okay, k is varying, n is your choice from outside. So, this summation will give you the sample, original time data sample at nth index, where n is within that range 0, 1 dot 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 n minus 1, which means I can reconstruct my finite leg sequence, endpoint sequence from these samples capital X 0, capital X 1 up to capital X minus 1, that is from these fellows only. I do not need the entire waveform, entire envelope. So, just I need storage for only n points. This is a fantastic result. Okay. So, what is xk? Xk is the called endpoint DFT. Here you are summing over n, k is fixed of your choice, k range was 0th sample, first sample or up to n minus 1th sample. So, find these xk's DFTs, then using them you can get back your xn. This is the inverse DFT. Please go through this, we will meet again in the next class, but I need full clarity on this. Thank you very much.